Howdy. So now we're finishing off with Signal Theory 3. We're starting with Learning Unit 6 and specifically Learning Unit 6.1. Now, in terms of the overview of the module, we're done with the design of infinite impulse response filters. And now finally we're taking a look at the design of finite impulse response filters. This learning unit will be divided into approximately three lectures. The first one being the present one, in which we'll take a look at FIR filter order selection, as well as a design technique, namely the design of a FIR filter based on a time domain window. And in the next lecture after that, we'll take a look at the Parkes-McClellan algorithm, and then finally minimum phase filters. Although it's listed here, the considerations to design computationally efficient FIR filters will just be mentioned but aren't for exam purposes. In terms of the specific lecture, we'll take a look at filter order, and that is also the topic of the first video of lecture 6.1. And then finish off with the technique as well as examples of how to design an FIR filter based on windows. Time domain windows, and specifically either fixed windows or adjustable windows. In terms of a bit of revision, the difference between IIR and FIR filters, beyond the mathematical expressions for their transfer functions, is that FIR filter is always stable. This is because it only contains a bunch of zeros. The price you pay for that is that you require a high order filter, and therefore it's computationally expensive. But another advantage is that the phase is always linear, and this is primarily an advantage where you are very interested in the time domain response of the filter, especially if you want to transmit pulses. Another bit of revision is the requirements of a filter are specified in terms of the two edge frequencies, the passband as well as the stopband edge frequency. It's important to be able to convert between the delta and the alpha values for both of these corner points, and always remember that in the design of IIR and FIR filters, the majority of the design takes place within the normalized frequency domain, in which half of the sampling frequency is represented by P. Okay, so the first topic now is how to choose the filter order. Now there are numerous techniques, and we'll start off with three formulas: Kaiser's formula, as Bellinger's formula, and Hermann's formula. Now Hermann's formula, it is in the textbook, and it's just a bunch of equations that you have to implement, preferably in a program. So it is there. So I'll just talk about Kaiser's formula as well as Bellinger's formula. Now, to estimate the filter order, you need to calculate the values of delta as well as omega. Now remember that the omega values within Kaiser's as well as Bellinger's formula are the normalized corner frequencies. So you have to normalize them with the sampling frequency itself. Also note the Kaiser's formula tends to underestimate the required order to meet the specifications, whereas Bellinger's formula tends to overestimate the required order. To give an example, let's determine what the filter order is for a low-pass filter that has to operate at a sampling frequency of 12 kHz with a passband edge of 1.8 kHz with a maximum ripple of 0.1 decibel, a stopband edge of 2 kHz with a maximum ripple of minimum ripple or minimum attenuation of 35 decibel. Okay, now I, as you probably could have guessed, opted for writing a bit of a Python code. In this code I just put in the given values. Then the first step is to calculate the normal values for delta P and delta S. In other words, the conversion from decibel through to the normal values, and then to normalize the edge frequencies, omega S and omega P. And thereafter the implementation is literally just that, just an implementation. And the answers that we obtain is that for, according to Kaiser, we need a 99th order filter at least, and Bellinger recommends a 107th order filter. You can try a 100th order filter and a 108th order filter, and the difference is based on what the final type of FIR filter is that you are aiming for. If you're aiming for a type 1 filter, then the order has to be even. Obviously, then the impulse response will be symmetric, and you can implement any type of filter. If you really want to have an odd order filter, then remember that the type 2 filter can't implement a high pass filter as well as the rest of the things depicted in the table. In the next video, we'll take a look at the design of a filter by means of the window technique.